Hello everyone, welcome back. Let's talk about another medium problem on Leetcode today. Implement trie or prefix tree. Problem number 208. This problem is part of Blind 75, a curated list of essential coding interview questions. You can find the full list linked in the description below. Be sure to check it out. Now to the problem. What if you could build secret sauce behind Google search autocomplete or the spell checker in your favorite word processor? Well, today we are going to build the core data structure that makes it all possible. A trie, pronounced as trie, also known as a prefix tree. It is a data structure used to efficiently store and retrieve keys in the dataset of strings. And the problem asks us to implement trie class, where the constructor initializes a trie object, and then the insert function inserts a string word into the trie, and the search function should return true if the word exists in the trie and false otherwise. And finally, the startsWith function should return true if there is a previously inserted word in the trie that has a prefix passed on into the startsWith function and false otherwise. For example, here we first create a trie and insert the string apple into it. And then we search for the word apple, and it should return true because search focuses on the exact match. Then we search for the word app, but it doesn't exist in the trie, so we return false. But if we search for the app as a prefix using the startsWith function, then we return true because the word apple, which is in our trie, does indeed start with the prefix app. And this is where the key difference between search and startsWith lies. Search looks for the exact match and startsWith look for the partial beginning match. And then continuing with our example, we then insert app into the trie and later search for it in the trie, which this time returns true because now the app exists in the trie. Now let's see how we can implement a trie. Trie is a tree-like data structure where each node represents a single character and a path from the root downwards forms a prefix. First, we initialize a trie where we create an empty root node. It is just the starting point for all the words. Now, let's look at the insert function. Suppose we have to insert the string apple first, and first character that we need to insert is A, and we check if the root node has a child for A, and it doesn't. So, we create a new node and link it to the root node and move our pointer to it. Next character we see is P, and P doesn't exist as a child of node A. So we create a node P and link it to the parent A and move our pointer to it. And we repeat the process for the remaining characters B, L and E. And after placing the final E, we mark this node with a boolean flag. Let's call it is_end of word to signify it is a complete word. And why is this flag necessary? Well, suppose we have to search for the word app in it, and we can see the path for this word clearly exists. But is app a word we actually inserted, or it is just a prefix of apple? And using this flag is how we know. After inserting the word apple, the node for P doesn't have this marker set. While if we have to search for the word apple, we can see that the flag on the node E is set, and hence we know that word apple exists in the trie. So using this flag, we separate prefixes from the actual words. And what does this trie node structure look like? Each node contains two key components, a collection of children. These are pointers to the trie nodes. This is often implemented as a hash map or dictionary. However, since the problem guarantees that the words and prefixes only contain lowercase English letters, we can use a more efficient array of size 26, where each index corresponds to a letter. For example, index 0 corresponds to A, 1 corresponds to B, and so on. And the trie node also has is_end of word flag, the boolean flag we discussed earlier, which marks if the path to this node is a complete word. And here, for example, this trie structurally looks like this. Basically, we start with the empty root and then in its children, we have the letter A along with the is end of word being false. And this node A has child P, which again has child P. And this child P has L as a child. And finally, L has the child E with is end of word being true. And because we are using hash maps, this structure allows us to check if the child character exists in just O of one time. For example, when we are at letter A, we can check if it has a child P in just O of one time, or if it doesn't have a child B also in just O of one time. So to summarize, first we define our trie node class. In Java, we are using a simple array of size 26 for the children, which is very efficient for a fixed character set like lowercase English letters. In Python, the idiomatic and more flexible approach is to use a dictionary. Also, you will notice that in Java code, trie node is a static nested class. This is a common Java pattern for encapsulation and memory efficiency. This isn't necessary in Python, where the standard practice is to have separate classes, following the flat is better than nested philosophy. Both node types also have the boolean flag is end of word. Then in the main trie class, we initialize a single root node which is our entry point. So we use two separate classes to follow the single responsibility principle. The trie class is the main builder that manages the operations, while the trie node class is just a simple data container for each individual node. Now let's continue further and insert a completely new word, Jamun, to see how a new branch is formed. So starting from the root node, we look for a child J and it doesn't exist. So we create a new trie node for J and link it to the root. And we move to the J node and look for a child A and it also doesn't exist. So we create it and link it and we continue this process inserting M, U and finally N. And at the node N, we mark it with the is end of word flag to true. Now let's look at the insert method. We start with the current pointer at the root and then we loop through each character in the input word. And for each character, we check if a path already exists in our children. If the path doesn't exist, we create a trie node and add it to the children of the current node. And then this is the key. We move our current pointer down to that child node. And after the loop finishes, the current pointer is at the node representing the last character of our word. We mark its is end of word flag to true. Now let's look at the search function, which is very similar to insert. Let's say we first search the word apple and again we start at the root node and see if it has a child A and it exists. Then we look if A has a child P and that also exists. And similarly, we continue to trace the full path PLE. And after successfully tracing the entire word, we have one final crucial check. Since search looks for the exact match, we must check if the is end of word flag on this final node E is set. And the answer here is true. So we return true for this search. Similarly, when we search for the word app, we successfully trace the path here as well. However, the is end of word flag on the final P is not set, so we return false. And for a word like orange, the search is even faster. We can check at the root itself that it has no child O, so we return false immediately. Now let's look at the search method. This is very similar to insert. Again, we start with the current pointer at the root. Then we loop through each character of the word. And at each step, we check if the child node for that character exists. If it ever doesn't, it means the word isn't in our trie. So we can return false immediately. But if it does, we just move our current pointer down the path. And if we complete the loop, it means the entire path for the word exists. But as it is an exact match, we must also check if the flag for this final node is set. If it does, this ensures we are matching a complete word. and hence we will return true and false otherwise. And finally, let's look at the startsWith function, which is where the try really shines. Here we will check for the prefix app, and just like search, we will trace the path app here. And for this method, this is all we need. We don't have to check the is end of word flag. As long as path for the prefix exists, we can confidently say there is a word in our try that starts with it. So we return true here. Now let's look at the startsWith method. It is most identical to search. We traverse a try based on the characters in the prefix. If we ever find that a character's path doesn't exist, we return false. But if we successfully finish the loop, it means the path exists. And for this method, that's all we need. So we will immediately return true. We don't care about is end of word flag here. And this startsWith function is what makes a try so powerful compared to more common data structures like list or map. In the list, for the insertion, we can just add a word to the list in just O of one time. But when we have to search for the word, we have to scan the list to find an exact match. But startsWith is a real problem. We'd have to iterate through every single word in our list and call startsWith method on it. And if the list had 1,000,000 words, we have to do 1,000,000 checks every single time, and this is too slow. And same is the problem with a data structure like hash map. Of course, with insert and exact search, a hash map is very fast as its lookup takes O of L time. Why? Because first we have to calculate the hash of a string, and for that the algorithm must iterate through all the L characters, and then the mapping operation takes O of one time. Hence, the overall time complexity of insertion and search will be O of L. However, with the startsWith implementation, say we have to check for the prefix app, we would still need to iterate over every key in the hash map and check them one by one. So in a way, we are back to the same problem as with the list. However, for the try, given n as the number of words and L being their average length, the time complexity of insert, search or startsWith is simply O of L, as we have to simply trace a path for a given word. This means performance is proportional to the length of the word L, not the total number of words in the try. And the space complexity will be O of n into L in the worst case scenario if no words share a prefix. For example, here apple and jamun don't share a prefix. In that case, we have to store every character of every word. However, space is often much better in practice thanks to the prefix sharing. For example, after storing apple, say we store the word app in the try, then it requires no new nodes, just flipping is end of word flag for letter P. So ultimately the try's key advantage is that its performance is tied to the length of our words, not the size of the entire dictionary. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.